Here is a question that comes up again and again in conversations about offshore wind. How do we know what these projects are doing to marine life underwater? And very often, someone in the room says, "We need acoustic data," and everyone nods. But when comes the follow up question, what kind of acoustic data is needed, collected and processed how, and for what decision? This is usually where the room gets quiet, especially when there are no hands on operators or technical experts in the room, because acoustic data sounds like one thing, but in offshore wind environmental monitoring, it is not one thing. It is at least two different pipelines. One pipeline supports near real time construction decisions. Should an activity start, pause, continue, or shut down? The other pipeline supports long term ecological assessment. Where are animals present? How often and weather patterns are changing over time? Same ocean, similar sensors, same basic raw material, underwater sound, but completely different decisions, data products, timelines, and users. That gap between saying we need acoustic data and knowing what that means in practice is what this video is about. So let's start with why acoustic sits at the center of so many offshore wind monitoring plans in the first place. Offshore wind construction can be loud underwater, and during construction, the dominant concern is often not what we can see from the vessel, it is what we cannot see below the surface. During foundation installation, impact vial driving sends intense sound into the water column. That sound can travel for kilometers depending on water depth, seafloor conditions, source level, oceanography conditions, and the noise attenuation systems being used. On the US East Coast, one of the most sensitive species is the North Atlantic right whale. This species is endangered. There are fewer than 400 individuals remaining, so regulators treat the risk to each animal very seriously. That is why offshore wind construction is not just a construction problem, it is also a compliance problem. Under the Marine Mammal Protection Act, the Endangered Species Act, and NEPA, the National Environmental Policy Act, agencies have to evaluate potential impact, require mitigation, and document monitoring before certain activities proceed. Monitoring is not just a nice to have. On this project, it becomes part of the legal conditions for constructions. Pile driving is the loudest and most tightly regulated activity, but it is not the only activity that uses protected species monitoring. High resolution geophysical surveys, subalum profilers, unexploded ordnance work, cable landfall construction, and some vibratory pile driving activities can also come with monitoring requirements. On the water, one of the most visible roles is the Protected Species Observer or PSO. PSOs scan the water for whales, dolphins, porpoises, seals, and other protected species. A lead PSO may coordinate visual monitoring and mitigation communication during operations. But visual monitoring has limits. You cannot see very far in fog, you cannot see underwater, and at night, even with thermal or night vision tools, visual detection becomes harder. This is why passive acoustic monitoring PAM is so important. PAM listens for vocalizing marine mammals. It can extend detection capability beyond what the person can see. It can operate during poor visibility, and it creates a record of what was heard, when, and where. A useful way to think about this is visual monitoring gives you especially specific observations when conditions allow. PAM gives you continuous listening records, including at night and during poor visibility. Neither replaces the other, they work together. Visual and acoustic monitoring are complementary, not redundant. But here is the key point: PAM is not one workflow, it is two major workflows that often get collapsed into the same phrase. Pipeline is construction monitoring. This is near real time and operational. Its purpose is not to produce a scientific paper 5 years after. Its purpose is to support decisions happening during operations. Can power driving begin? Should the activity be delayed? Does an active sound source need to shut down? During foundation installation, acoustic monitoring does not operate in isolation. It works alongside visual monitoring by PSOs. Visual observers can confirm animals at the surface, estimate distance, identify behaviors, and sometimes confirm species. Acoustic systems can detect vocalizing animals beyond visual range at night or in poor visibility. One sees, one listens. Together, they reduce the chance that an animal is missed. The raw data from a hydrophone is a waveform pressure over time, but the decision maker does not need a giant audio file. The decision maker needs a data product. Was a target species detected? Was it possibly detected? Was it not detected? For reporting into data systems, those detection results are represented with terms like detected, possibly detected, not detective. Operationally, the difference between detected and possibly detected can matter less than you might think. For a highly protected species like the North Atlantic right whale, a possible detection is often treated conservatively. If the acoustic detection might be inside the relevant mitigation zone, the monitoring team may take a precautious approach. Under the approved monitoring plan, if a protected species is detected within the applicable clearance zone before operations begin, operations may be delayed until the species exits the zone. If operations are already underway and the protected species is detected within the applicable shutdown zone, the source may need to shut down until the species exit. Both the lead PSO and PAM operator may have authority to call for a delay or shutdown depending on the project authorization. And when that call is made, the required mitigation action happens first, and disagreement is discussed afterwards. This is the first major acoustic data pipeline: fast, operational, conservative, and tied directly to mitigation. The decision is immediate, the cost of the decision can be high, and the tolerance for ambiguity is low. Now, let's shift to the second pipeline. This one is long term archival monitoring. It may start before construction, sometimes years before. Hydrophones are deployed on the seafloor, on moorings, or buoys, or on mobile platforms. They record whale calls, vessel noise, ambient sound, and the broader soundscape. But nobody's using those archive recordings to call an immediate shutdown. That is not the purpose. The purpose is to understand patterns over time. Where are whales present? What percentage of days include detections? How does the presence change seasonally? How does vessel noise vary? Is the acoustic environment changing before, during, or after construction? And across multiple projects, are there regional shifts that matter for management? This pipeline runs on a very different timeline. Instead of minutes, it runs on months and years. Instead of a PAM operator making near real time mitigation judgments, analysts retrieve instruments, download recordings, apply calibration information, run automated detectors, review results, and summarize detections into higher level data products. The data product might be something like North Atlantic right whale detected 18% of monitored days at this location. This is where the NOAA and BOEM minimum recommendations are useful. They frame PAM as more than just a construction mitigation tool. PAM can support species present monitoring, soundscape monitoring, mitigation, behavioral, and distributional assessment, and long term management. Same raw data, underwater sound, but a completely different question. Pipeline 1 asked, is there an animal close enough that we need to change operations now? Pipe 2 asked, what patterns are emerging over time across the ecosystem? That is why saying we need acoustic data is not specific enough. We have to ask for what decision, on what timeline, for which user, at what spatial scale, and at what level of processing. Now, let's talk about quality control and data sharing. Because once acoustic data is collected, the next question is how do we make sure that the data is usable? This data can influence construction delays, mitigation actions, agency review, public trust, and long term science. So, quality control is not just a technical step, it is part of the credibility of the entire monitoring program. Each pipeline has quality checks, but the checks are different because the failure modes are different. In a construction PAM plan, the data pipeline is built around real time mitigation. A PAM system transmits or processes the acoustic data. A PAM operator reviews detections in real time. The detection is communicated to the mitigation team. And if the detection meets the conditions in the approved monitoring plan, it can support a delay or shutdown decision. But that real time decision is not the end of the data pipeline. The detection still has to be documented, checked, submitted, and archived. This is where timing matters. Near real time construction PAN has an extra urgent reporting layer. If a North Atlantic right whale is detected in near real time, that observations is submitted to NOAA using the real-time North Atlantic right whale acoustic and visual observation data template. The report is submitted immediately if possible or no later than 24 hours after the observation. So think of the 24-hour report as the urgent agency notification layer. It is for rapid right whale awareness and regulatory communication. It is not submitted through PARS. PARS is a different pathway. PARS stands for Passive Acoustic Reporting System. It is NOAA's structured detection data repository for passive acoustic monitoring data. And data submitted through PARS can be displayed on the passive acoustic citation map. NCEI, NOAA's National Center for Environmental Information, is where raw acoustic recordings can be archived. So the simple way to think about it is this. The 24-hour report is unique to near real-time monitoring. Structure detection data for parse and raw acoustic recordings for NCEI follow a longer clock and depend on project requirements. For example, in the Sunrise Wind Turbine Pipe Driving PAM plan, the full construction PAM data set, including acoustic detection data, metadata, and recorded location information from real-time hydrophones, must be submitted within 90 calendar days after pile driving has ended and the instrument has been pulled from the water. The full acoustic recordings from those real time hydrophones must also be submitted to NCEI for archiving within that same 90-day window. So the 24-hour report and the 90-day submission serve different purposes. For archival monitoring, the QC problem is different. The timeline is longer, and the risk is not just a missed real time communication. The risk is that months of recordings cannot be integrated correctly later. So, archival QC focuses on metadata, calibration files, deployment records, file completeness, and recording gaps. Analysts need to confirm that the files match the deployment metadata. They need to document interruptions in recording, and they need enough calibration and metadata information so another user can understand what was recorded, where, when, and with what instrument. As with construction PAM, long-term archival PAM data can produce structured detection data for parse and raw acoustic recording for NCEI. So the construction PAM asked, do we classify and communicate the detection correctly in time to support mitigation? Archival PAM asked, can this long-term data set be trusted and interpreted months or years later? Same acoustic detection, different reporting pathway. And that is one of the main reasons offshore wind data management is difficult. It is not only a sensor problem, it is also a pipeline problem. That same basic structure applies across many offshore wind monitoring modalities. A sensor or survey produces raw observations. Those observations are processed into a data product going through quality control. Then it is reported, archived, visualized, or used to support a decision. You see versions of these structures in visual surveys, aerial surveys, acoustic telemetry, benthic monitoring, fisheries monitoring, and emerging tools like environmental DNA. But the details are different. Each modality has its own sampling design, metadata requirement, QC steps, data standards, regulatory context, and users. And increasingly, it applies to integrated platforms. For example, a single mooring might carry a PAM hydrophone and an acoustic telemetric receiver. One sensor listens for whales, another detects tagged fish or sea turtles. The platform may be shared, but the data pipelines are not identical. This is why interoperability matters, not just because we want data in the same format, but because offshore wind monitoring is becoming a network of sensors, platforms, portals, and decisions. If those systems cannot talk to each other, then the value of the monitoring is limited. And if we do not understand the purpose of each data stream, we may collect data without producing information that anyone can actually use. So the next time someone says, We need acoustic data to understand the impact of offshore wind on wells. As a follow-up question, do we mean real-time mitigation data? Do we mean archival recordings? Do we mean data for a shutdown decision or a long-time ecological assessment? Because that one phrase, acoustic data, can hide multiple pipelines, multiple decision makers, multiple deadlines, and multiple archives. For a data provider, the key is to understand the purpose of the data before collection begins. What is the required data product? What metadata must travel with it? What QC steps are expected? Where does it need to be submitted and when? For a data user, the key is to understand how the data were collected and processed before turning them into conclusions. A detection map is not just a map, it is the end of a long chain of sensor designs, deployment, calibration, detection method, quality control, and reporting rules. I hope this video helps you better understand acoustic data pipelines and the data ecosystem and ask the right questions before turning data into decisions.